Here's a quick overview of our new paper titled Breaking Reflection Symmetry, Evolving Long Dynamical Cycles in Boolean Systems. We study Boolean networks, which consist of a finite set of nodes, each characterized by their own state. These Boolean states are binary, either 1 or 0, which we'll refer to as on and off for ease of understanding. These networks evolve in steps where all the node states are updated at the same time. Nodes are linked through two kinds of edges: excitation, depicted by green arrows, and inhibition, indicated by red arrows. Edges become active only if their originating node is on. The updating mechanism for the node state relies on a threshold function. A node switches to the on state at the next step if it receives more activated excitation edges than activated inhibition edges. If the number of incoming activated edges is equal, the node's state turns to off. Boolean networks play a pivotal role in biology by simplifying complex molecular interactions into binary states, facilitating the modeling of intricate regulatory networks and aiding our understanding of emergent biological phenomena. Interestingly, their dynamic can be influenced by the smallest of changes in their topology. For instance, in this network, treating the orange edge as inhibitory leads every initial state to eventually converge to the same stationary state. Conversely, if this edge is considered excitatory, a prolonged cyclic pattern emerges. These cycles, while uncommon and delicate, are important for a lot of physical and biological systems. In this study, we try to understand how they emerge from the topology of the interaction network. Here's an example of a network that exhibits an exceptionally long cycle relative to its size. With just 4 nodes, it sustains a cycle of length 10. It's one of the 2 optimal networks of this size when optimizing for cycle length. Our findings suggest that long cycles are associated with what we term dynamical reflection symmetry in the interaction network. Dynamical reflection symmetry implies that if a state A evolves into a state B in a given network, then the inverse of the state A will evolve into the inverse of the state B, where in our context, opposite means that 0 is mapped to 1 and vice versa. We found that networks generating symmetric transitions like these tend to lead to long cycling behavior. Additionally, we identified the specific structures within the network that disrupt this symmetry. In identifying the important role of dynamical symmetry in Boolean networks, this work suggests strategies that can be used to engineer dynamical features. In particular, we have shown it is possible to enhance or suppress cycling behaviors by altering only a small subset of edges in a system's interaction network topology. As applied to complex biophysical systems in pharmacology and microbiology, this understanding may aid the design of targeted diagnostics and therapeutics.